Now let me teach you fundamental fact just for fun. It won't be very useful. Here it is. So when you have this linear situation, and this is a matrix of integers, in our case in Bernoulli, then what this does is if this field is in a hypercube, then what this matrix does, it takes hypercube and it's a matrix, so it deforms it and it stretches it in what's called fundamental parallelepiped. Straight lines remain straight lines, but things get stretched. And each periodic point that you're trying to find, depending on your instruction M, has to sit on integer lattice. And so this product has to be an integer, and then you have to slide the result by this instruction to get a 0. So that's what it looks as a formula. And amazing thing about it is the number of solutions of this problem, how many distinct solution is the number of integer points within this parallelepiped. The determinant of this Hill matrix, which I'll call Hill determinant, counts this number. The volume is just the number of solutions. That's a fundamental fact. To give you a picture, if you have period 2 systems, so 2 lattice sites repeated on infinity, then Hill matrix is just 2 by 2, and you're able to visualize it. The edges of the unit matrix say either 0, 1, or 1, 0, these 2 vectors. You multiply things by parallelepiped, you plot it, so you start in a unit square. What comes out is a fundamental parallelepiped, and what do you know? Its volume is 3 times the volume, unit volume. And all these points become periodic points of the original problem, but the volume actually measures number of solutions. And that turns out to be useful even in d-dimensional spatiotemporal calc, much more rich problem than this Bernoulli problem. So in 3 dimensions, you can still draw a picture. There's a cube in 3 dimensions. You bang it by the orbit-Jacobian Hill matrix, and you find parallelepiped, which is 3-dimensional, and then you count points on its surface, and everything works as it should. The fundamental fact is still true. It still works, even